Okay, let's just dive right in. Welcome to today's Explainer, where we're going to completely unpack the fundamental laws that govern, well, absolutely every single movement in our universe. From the tiniest pebbles skipping across a pond to those massive planets orbiting the sun, the whole shebang plays by the exact same hidden rules. And today, we're going to figure out exactly how those rules work.
To kick things off, I want you to picture a classic magic trick. You've definitely seen it, right? A magician yanks a tablecloth right out from under a fully set dining table, and somehow all the dishes perfectly stay in place. Or, hey, think about your own daily commute. Why do you immediately lurch forward in your seat when a car slams on its brakes? It feels like magic, or maybe just really bad luck, but there's actually a very specific physical property pulling the strings here.
So the secret behind both of these phenomena is a little concept called inertia. Put simply, inertia is an object's natural resistance to any change in its state of motion. Basically, what this means is that objects desperately want to keep doing exactly what they're already doing. If they're just sitting there, they want to stay sitting there. If they're moving, they want to keep moving. And this stubbornness, it's directly tied to mass. The heavier something is, the more stubborn it is about changing what it's doing.
So here's our agenda for today. We're covering 5 main areas. 1. Understanding force and motion. 2. The magic of inertia. 3. Measuring force with F equals ma. 4. Action, reaction, and gravity. And finally, 5. The equations of motion.
Section 1. Understanding force and motion. Let's look at the basic push and pull.
Now, there's a really crucial distinction we need to make right up front between balanced and unbalanced forces. Force itself is just a physical cause that changes, or at least tries to change what an object is doing. But if you have balanced forces, meaning the forces acting on a body are perfectly canceling each other out, there is absolutely zero change in motion. None. It's only when those forces are unbalanced, when they're not equal, that an object is actually going to change its speed or direction, kind of like when you kick a football. This setup brilliantly illustrates balanced forces in action. Just look at the two figures here. Even though they are both putting in a ton of effort, pulling on that spring balance with exactly 100 newtons of force in total opposite directions, they completely cancel each other out. Because the forces are equal and opposite, the net force is just 0. The meter reading stays completely flat and absolutely nothing moves. Crazy, right?
Moving on to Section 2. The magic of inertia. Why objects resist change.
All right, the big takeaway here is that inertia actually comes in 2 distinct flavors. Inertia of rest is the tendency of a thing to just remain totally stationary unless some outside force messes with it. This is exactly why a parked car doesn't just roll away on its own, and why those dishes stay perfectly put during the magician's tablecloth trick. On the flip side, we have inertia of motion. This is an object's tendency to just keep moving at a constant speed. It's the exact reason a hockey puck will glide so smoothly across an ice rink in a perfectly straight line until friction, our external force, finally slows it to a halt.
And you guys, this isn't just dry textbook theory. It has massive real-world applications. For example, engineers use the inertia of rest to design vehicle safety systems. Seatbelts are specifically designed to catch you because your body, thanks to the inertia of motion, literally wants to keep flying forward when your car suddenly slams on the brakes. And in sports, athletes rely on the inertia of motion all the time. When a long jumper takes that huge run-up, their forward momentum just keeps carrying them forward even after their feet leave the ground, pushing them way further across the sand.
Okay, Section 3. F equals ma. Measuring force.
This principle right here is basically the absolute golden rule of classical mechanics. It proves beyond a shadow of a doubt that force, mass, and acceleration are permanently tangled up together. Simply put, it tells us that the heavier an object is, the more mass it has, the harder you are going to have to push it to change its speed.
So let's break down the actual math of F equals ma. Acceleration is directly proportional to the applied force, meaning push harder and it accelerates faster. Pretty intuitive, right? But it is inversely proportional to the mass of the body. So if that object gets heavier, that exact same push is going to give you way less acceleration. This creates this just perfect mathematical balance that lets us predict exactly how any object will behave the second a force hits it.
Let's actually put a number to this to make it totally concrete. Say you apply a net force of just 1 Newton to an object that has a mass of 2 kilograms. What happens? Well, you just divide the force by the mass. The math guarantees us it will accelerate at exactly 0.5 meters per second squared. It is literally that predictable, every single time.
All right, Section 4. Action, reaction, and gravity, the universal forces.
Now, I know you have definitely heard this phrase before, but guys, this isn't just some deep philosophical saying about life. It is a literal, inescapable law of physics. Forces never, ever exist all by themselves. They always come in pairs.
To see how incredibly vital this is, just think about taking a simple walk down the street. When you step, your foot pushes backward on the ground, right? That's your action. Well, the reaction is the ground pushing forward on your foot, which is the exact thing that actually propels you forward. Without that reaction force, walking would literally be impossible. It's the same deal with a rocket launching into space. It blasts all that hot gas downward, the action, so the equal and opposite reaction is the massive thrust shooting the rocket upward, totally defying gravity.
And actually, speaking of gravity, it operates under these same beautifully predictable rules. Newton's law of gravitation states that every single body in the universe attracts every other body. No exceptions. This force scales way up depending on the mass of the objects, which is exactly why the Earth pulls you down to the floor so strongly. And it drops off super fast as the distance between the two objects increases.
Let's test that concept out with a quick thought experiment. So, if gravity drops off with distance, what exactly do you think happens to the gravitational force between two planets, or any two bodies, if you were to magically cut the distance between them right in half? Well, because gravity is inversely proportional to the square of the distance, messing with that gap has a massive mathematical impact.
The answer is 4. Yep, by having the distance, you don't just double the gravitational pull. Because the distance is squared in the denominator of the equation, the force actually becomes 4 times as strong. Meaning moving things just a tiny bit closer together massively amps up the invisible pull they have on one another. It's wild.
And finally, Section 5, the equations of motion. Let's predict reality.
If you want to read the universe's source code, you just need to learn these 5 fundamental variables. U is your starting speed, or initial velocity. V is your final velocity. A is for acceleration. T is the time elapsed. And S is displacement, which is basically distance. Once you've got a handle on these basic variables, you literally have the vocabulary to track, map, and predict the exact location and speed of any moving object.
This graph does a beautiful job illustrating those variables in action. Check out the line, that upward slope from point A to B. That shows positive acceleration, meaning the velocity is steadily increasing over time. Then, that flat top section right between B and C represents a constant velocity. And remember what we talked about earlier? Constant velocity means there is zero net force acting on the car. The forces are totally balanced. After that, the downward slope from C to D shows deceleration or retardation as the car slows all the way back down to a complete stop.
The best part is you don't have to blindly memorize these equations. They follow pure, elegant logic. Like you can easily derive the first equation of motion, v equals u plus a, all by yourself. You just start with the basic definition that acceleration equals the change in velocity, so that's final minus initial, divided by time. Then you multiply both sides by time and simply rearrange the terms to isolate the final velocity. Boom, you get v equals u plus a. It's just beautifully stacked logic.
Wow, we have covered a ton of ground in today's explainer, from magic tablecloth tricks to literal gravitational fields. Now that you've seen firsthand how math can completely demystify the physical motion in our everyday lives, it really makes you wonder, right? If forces in motion are this perfectly mathematically mapped out, what other hidden frameworks and invisible laws are out there just waiting to be explored? Keep that curiosity alive, guys, and keep looking for the equations hiding in plain sight all around you. See you next time.